Hello students, welcome to JCE Connect series of lectures. In previous class we have solved some numerical problems on design of beams. Uh, in this session also we'll continue some more design problems on beams. So let us take one more problem, that is design a cantilever beam built into a concrete wall. It supports a dead load of 25 kN per meter and live load of 15 kN per meter. The effective span of the beam is 4 meter and the beam is laterally supported. Okay, this is the problem given, that is the cantilever beam is given. As you know, the cantilever beam, the one end is fixed, other end is free, and this beam carrying a UDL, the both self weight as well as the self weight as well as the live loads, that is a dead load and live loads are given, and the span of this cantilever beam is 4 meter. Then the total UDL 25 plus 15, then the factored load will be, make it factor that multiply it by 1.5 will becomes of 60 kN per meter. Then as you know, the bending moment for this cantilever beam can be given as, that is maximum bending moment will be WL square by 2. Then we get for WL square by 2 480 kilonewton meter. Then next you have to calculate the required section modulus. The required section modulus, that is the strength of the section required, ZP is equal to M into gamma MO by Fy. Substitute the value of bending moment here, then the gamma MO, then the Fy. We get this much value, that is 2112 into 10 raised to 3 millimeter cube. Then you have to choose the section in such a way that the value of ZP should be more than this value, that is required value. So let us try ISMB 550 at 103.7 kg per meter. You have to choose the section from the IS 800 2007 and note it down all the properties of that section, that is depth of the section, width of the flange, thickness of the flange, thickness of web, elastic section modulus and plastic section modulus, as well as moment of inertia about the major axis which required for that is the check for deflection, then the root radius of that section. Then after this one, do the section classification, calculate the individual element ratios. Then here note it down the epsilon value, that is 1. Then the outstand of flange width, B is BF by 2. How it epsilon comes? Epsilon value will be root of 250 by Fy. Then calculate outstand of flange, then the depth of web. This is the I section, this is the depth we to take, that it will deduct from the depth, that is whole depth, but minus 2 times of flange and also minus the root radius of the section. Then calculate the ratios of individual elements. Then here we are getting the flange to width, flange to thickness ratios, width to thickness ratio of flange, that is 4.92, which is less than 9.4. Then depth to thickness of web, then that is we are getting 42.44, which is less than 84, which represents the section as a plastic section, that is the section is classified as a plastic section. Then for a plastic section the value of beta will be 1. Since the depth to thickness ratio of web is 42.42, which is less than 67, hence the check for web buckling is not required. This is one. This also you have to do the check, that is whether the web buckling, check for web buckling is required or not. You have to do the check. Okay. Then after this one, next is check for shear capacity. So what is the maximum shear force per cantilever beam carrying UDL that is a WL 60 into 4, that is 240 kilonewton. Then design shear strength of the section, calculate design shear strength of the section, that is the chosen section. How much is the shear capacity of that section? The equation will be VD is equal to Fy divided by root 3 into gamma MO into H into TW. Substitute all the values here, we get 808.29 kilonewton, which is more than 240 kilonewton, hence safe. Then also do the check for high shear or the low shear. For that we will take the 60% of the design shear strength. Then the 60% of the design shear strength will be 484.97 kilonewton, which is greater than 240 kilonewton. Hence this is the case of low shear. For the low shear case, the MD value will be beta B ZP into Fy divided by gamma MO. Substitute all the values here. After substituting, you will be getting 616.35 kilonewton meter. And as per the code, the value of MD should be less than or equal to 1.5 into ZE into Fy divided by gamma MO for the cantilever beam carrying UDL. Then this value also you have to calculate. We are getting here as 804.47 kilonewton meter. Then compare these two values, whichever is the least one, that is the design shear strength, design bending strength, that is design bending strength will be 616.35 kilonewton meter, so which is greater than 480 kilonewton meter, hence the section is safe. Also do the check for deflection. Then the maximum deflection, the cantilever carrying UDL will be delta max. Delta max will be WL raised to 4 by 8 EI, where EI is the flexural rigidity. Substitute the value of E here, that is 2 into 10 raised to 5. W as we know, then there is a working load to be taken. Then I also we have taken from the steel table. Then we get the maximum deflection as 9.86 millimeter, 9.86 millimeter. But the allowable deflection is for a cantilever beam will be L by 150. Then we get as 26.67 millimeter, which is greater than 9.86 millimeter. Hence the chosen section is safe against the deflection. Okay, so this is about cantilever beam design. Let us take one more design example, that is given here as design a steel beam section for supporting a hall. For the following data, assume steel of grade Fe410 and the clear span here given as 6.5 meter, the end bearings 200 millimeter and center to center spacing of beams 3 meter, imposed load on the beams 12 kilonewton per meter square. So this is the problem given. So let us design this problem. So here the dead load, that is inclusive of self weight, also given, that is 3 kilonewton per meter square. Then the compression flange of the beam is laterally supported throughout, that is the compression flange is restrained against lateral buckling. So here Fy will be 250 MPa, then the gamma MO is 1.1, gamma MF is 1.5. So this is a simply supported beam given, the clear span given here as a 6.5 meter, then the bearings, that is a support thickness given as 200 millimeter on either side the bearing, then the center to center of this beam will be 6.7 meter. Effective span, that is L will be the clear span plus bearing, then L will be 6.5 plus 0.2, 6.7 meter. The total UDL per meter square will be 12 plus 3, 15 kilonewton per meter square. Then the total UDL per meter will be this total UDL per meter square multiplied by the center to center spacing of beams. So these beams are being designing for a particular hall, and the beams are spacing at 3 meters center to center. Then the total UDL per meter run will be 15 into 3. that is 45 kilonewton per meter. Then the factor it, make it factor, you will be getting total UDL per meter into gamma f, that is factor of safety, we get as a 67.5 kilonewton per meter. Then maximum bending moment for a simply supported beam carrying UDL will be WL square by 8. Calculate maximum bending moment, we get as a 378.75 kilonewton per meter, sorry, kilonewton meter. Then once we get the bending moment, then calculate the required section modulus. Then based on this section modulus, so we have to choose the section, calculate ZP m into gamma mu divided by Fy. Then 37, we get final value as 166.54 into 10 raised to 3 millimeter cube. Then let us try the section, that is ISLB 500 at 75 kg per meter. And you have to choose a section in such a way that the section modulus should be higher than the required. Then note down all the properties of the chosen section, that is the depth of the section, width of the flange, thickness of the flange, thickness of web, elastic section modulus, then the plastic section modulus, then the moment of inertia, then the root radius, all should be noted down. Then next will be what? Section classification. Do the section classification based on the individual element the ratios. As per the code, the value of epsilon will be 1. Then outstander flange width, note it on the outstander flange width, and you know how to calculate the outstander flange width, and it is been given in a code also how to take. And based on the individual element ratios, that is the flange is one element and web is one element, you have to take the individual element ratio, that is the flange width to thickness ratio for flange as well as the depth. Then calculate that ratios. Then after calculating the ratio which are lying lesser than the permissible limits, hence the entire section, that is a chosen section, is classified as a plastic section, and for the plastic section the value of beta will be 1. Okay, so this entire, whatever the section is chosen, that entire section is lying in a plastic, hence the value of beta will be 1. Then do one more check whether the web buckling is required or not. For that you have to take the depth to thickness ratio of web, which is less than 67 as per the code. Then the check for web buckling is not required. And next is the check for shear capacity. Then the maximum shear force for the simply supported beam carrying UD will be WL by 2. That is the reaction. We get a maximum shear force as a 226.13 kilonewton. And also calculate the design shear strength of the section, that is chosen section. The design shear strength for the chosen section will be VD is equal to Fy divided by root 3 gamma mu into H into TW. This is the area. Then calculate the design shear strength, that we get as a 603.59 kilonewton, which is greater than 226.13 kilonewton. Hence the section is safe. Then next check is whether the chosen section is lying in a high shear or the low shear. For that you have to take the 60% of the design shear. So when we calculate 60% of the design shear, we get as a 362.15 kilonewton, which is greater than 226.13 kilonewton. Therefore the case is of low shear. Then the design bending strength. The design bending strength will be, for the low shear case, this is beta into ZP into Fy divided by gamma mu. Substitute all the values here, then we get as a 403.1 kilonewton meter. And this MD should be less than or equal to 1.2 into ZE into Fy divided by gamma mu. This is for the simply supported beam carrying UDL. Calculate this value also. So when you calculate this value, then we have to compare with the design bending strength MD. Whichever is less, that is to be finally considered as a design bending strength. So in this case, for MD value will be 403.1 kilonewton meter, which is greater than 378.75 kilonewton meter. Hence the chosen section is safe in carrying the bending, that is bending strength. Then the next check you have to do is a check for deflection. The check for deflection is very very important. Check for deflection. For that, calculate first maximum deflection of simply supported beam carrying UDL. The maximum deflection equation can be written as 5U divided by 384 into WL dash to 4 by EI, where W to be taken as a working load 45 kN per meter. Calculate the delta max, that is 45 into that is delta max WL raised to 4. Then calculate that one, that is we get as a 15.3 millimeter. Then the permissible deflection as delta equal to L by 300, that is we get as 22.33 millimeter. Then the delta max will be 15.3, which is less than 22.3 millimeter. Hence the chosen section is safe against deflection. I hope you understood this design problem. So in this design problem I just taken bit different from previous problem. Similar type of problems you practice it, and we'll continue again still more problems in next class. Please practice these kind of problems. Thank you.